Okay, I'm not going to teach you everything. I'm not going to explain everything. I'm just going to explain the things that at this point you should probably know for the introductory physics course. Okay, and I'm just going to start with the way I do it and go over basically all the main equations. Um, and then so you can see where kind of you need to be at. So the first is the definition of position, velocity, and acceleration. So we define if we have an in one dimension, if this is the x-axis, and these are your x values, so you have an object there and it moves over there, then this would be, let's say, x1, this is x2, that's the position. The velocity is defined, the average velocity is defined as the change in position over the change in time. And so from this, I can say x2 equals x1 plus v average delta t. And that's for an object. It doesn't really matter if it's moving or not. I mean, it does matter if it's moving. Well, maybe if it's not. But even if it's accelerating, this still works as long as you use the average velocity. And then we get to the definition of acceleration, change in velocity over change in time. And you get v2 equals v1 plus a delta t. And this is in one dimension. And then if you use this along with v average equals v1 plus v2 over 2, then you get the following kinematic equation: x2 equals x1 plus v1 delta t plus 1/2 g delta t squared. Okay, now forces. So this is the fundamental nature of force and motion. We have Newton's law, Newton's second law. It says that F net in one dimension, I'm going to write it as a vector, F net equals ma. So this says the total force on an object is proportional to the acceleration of the object. So if you have a constant force, it constantly accelerates. And the proportionality constant is the mass. Now there's another way to do this, and it's called the momentum principle. And remember, if it's PAL, that's a person, a principal. And this is for me. It has nothing, don't worry about that. So this says that momentum is mass times velocity, and it's a vector. And then we can write F net as delta P over delta T. So these two things are, in most cases, equivalent. But there's some reasons for this that you may not really fully understand yet. But I kind of like this one better. Now, there's one other very important thing about forces. So let's say that these two are masses and they have a gravitational interaction towards each other. Then this is A and this is B. The force of B on A is equal to negative the force of A on B. Forces come in pairs. That's an important aspect of the force model. In a lot of textbooks, they call this the third law. Just be careful if you say for every action there's an equal and opposite reaction. There's some problems with that terminology that have to do with how Newton kind of put these things down. You got to realize that when Newton did Newton's laws, if you want to say them that, there was no word for momentum. He didn't have the words to describe things, so it really made it difficult. It was a really tough position. Okay, so that's forces. Let's talk about vectors. So a vector is a variable with more than one piece of information. So if this is the x, y coordinate coordinates, then we can describe position as a vector r. R equals rx, ry, rz. And this is one way to do it, to describe the components of a vector. Some other places do it like this: rx x hat plus ry y hat plus rz z hat. I don't see, it's not, this is the way the book does it. This is the way I do it. There is this that's less well used. J hat plus RZK hat, IJK. Okay. But either way, this tells you how much it goes in the x direction, how much it goes in the y direction and how much in the z direction, rx, ry. And then you should be able to find the magnitude of a vector. You should be able to find the unit vector of a vector, which is important when we calculate gravitational fields and forces. This is the vector r divided by the magnitude of r. You should be able to add vectors. R1 plus R2, you should be able to do that. You should be able to subtract vectors. Delta R equals R2 minus R1. You should be able to multiply a scalar times a vector. So you could do delta t times A, delta t times V. Okay, so this V1 delta t, that's a vector and that's a scalar. You multiply them together. And if this is the same angle theta, you should be able to find the components. But I'm not giving the whole vector review. Those are the kind of things that you should know. So with that in mind, we can go back to the definition of average velocity. It's a vector, v average delta r over delta t. A average, the acceleration is delta v over delta t. And then we have r2 equals r1 plus v1 delta t plus 1/2 a delta t squared. And that's the kinematic equations. Okay, now let's just talk about the last thing, which is all these special forces that we have. So I'm going to just describe the equations for different forces. Some of them are easy, some of them are not so easy. Let's start with the easiest one, Fw, I'll call it. The weight on the surface of the Earth is mg, where g is equal to 0, negative 9.80 newtons. Then I have the real gravitational force. I'll call it F big G is negative G. M1 M2 R hat over the magnitude of R squared. So this is the gravitational constant. These are the two masses interacting. This is the vector distance between their centers, and that's a unit vector from one to the other. So it makes it a vector. There is the spring force. F spring equals K times S. I'm going to write it as a scalar because it's just easier that way. But this K is the spring constant. I've gone too fast. I was thinking about S. And S is the stretch or compression. And then the spring force will be in the opposite direction of the compression. I don't write it as a vector because there's a problem there if you just write it S, unless you write S as a vector, so I don't do that. These are the three easiest things to calculate because we actually have formulas for them. Then there are things like tension, normal force. Those are hard to calculate because these are forces of constraint. They depend on the situation that you have. The tension is always in the direction of the string, but other than that, it's pretty hard to deal with. We have the frictional force, F friction static, is less than or equal to mu s times n. So this is a force parallel to the surface that opposes relative motion, and it can be anything up to this coefficient mu times the normal force. And then we have the kinetic friction force, F friction kinetic, is equal to a different coefficient times the normal force. I'm trying to think of any other really important forces at this point. I think that's pretty much it. And then we can use these forces with the momentum principle and Newton's second law. And so this is a special case of Newton's second law. F net equals 0. This is what we call equilibrium. And so all the forces acting on an object would have to be add up to 0. But there's a lot there. Okay, I don't want to oversimplify this or give you the impression that it's not super simple. But I'm just trying to show you the things that you should be able to understand. If there's some of the stuff that you're like, I'm not clear about, let me know. Or go back and watch the videos on that or read the corresponding part of the textbook. Okay.